This time I will design a square called a square footing. So from your book I am picking problem 12-8. The reason I am picking because the answer is not given here. Okay, so what is this? Column is 12 inch by 12 inch square column, dead load 100, live load 80 key, A prime C 3000 K psi or 3 ksi, and FY 60 QA allowable soil pressure. The amount of pressure soil can give to my foundation is 5 uh, oh yes 5 ksf, that means 5000 pound per square feet. And then the distance from bottom of the footing to final grade is 5 feet, that means 60 inch. So we will design this footing, the column size given, load given, material properties given, soil strength given, and the depth of the foundation is given. So we will start designing this footing. I hope that before this video you saw the uh, wall footing design. It is similar, except there's very small change that is called punching shear. So we will discuss when that time will come. So at the beginning, what is our duty? Our duty is to assume a footing size, not the plan view, the depth. So at the beginning we are assuming 18 inch footing, so that our D will be 13.5. The rest of 3.5 will take care of the clear cover from the center of the bar. So now if you know that if you know like an approximate size, or based on your experience, if you know the what the size should be, then your guess will be like very perfect from the beginning, or very good guess. If you do not know, just start from any number, and then in your second trial you can revise it. And let me tell you again that design is never a one-way process. It is a loop. You will assume some, check these, again you will come back because your size may be over designed, maybe under designed. So you need to come back again and again in your real life. In your exam, do not need to do second trial. Just first trial should be good, and just tell after the design that something is going bad or something is not going good. So you will revise it. Okay, so whatever it is, you know that. So we are assuming 18 inch footing. Then we will calculate the effective soil pressure. Effective soil pressure, what is this? You can see the foundation is here. This is QA. This is QA. The allowable soil pressure is allowable soil pressure, but some pressure will be balanced by the weight of the concrete and weight of the soil. So from this we need to deduct the weight of this and weight of this. So that is we are doing here. Again, before going there, we assume 18 inch footing depth, and then this will be 42 inch because total is 60 inch. So we will minus that 18 inch. That means if I write here, so 18 is divided by 12 foot, and unit weight of concrete is 50 pound per cubic feet, minus 42 inch of soil. This 12 will take care of inch to feet. Then soil weight, say 100 pound per cubic feet. That will give me the effective soil pressure. Effective soil pressure. Okay, we will see that. It is not here. Yes, it is here. So you can see here 5000 is our given allowable soil pressure, minus 18 inch of concrete, and then 242 inch of soil pressure. 100 psf is a good number for soil. Then it is coming 4.425 psf. So this is the effective. Then the area required is load divided by QE. We know that size of the foundation is taken as based on the service load. We do not factor it. Our live load given as 100 kip, dead load 80 kips, divided by QE effective. That will give me the size 40.79 feet square. So we are assuming 6 feet 6 inch or 6.5 feet, 6.5 feet footing. My area will be 42.25, very close. You can provide more, you cannot provide less. So we are providing slightly more to make it a round number. So if you just use 6 feet, 6 feet, it will be 36. That will be like less. And 6.25, 6.225 feet, maybe okay. I do not have any calculator. Let me check. Okay, so if I use 6.25, then it will be 39 feet square. So not good. So to make it round, we are assuming this. Okay, now we will calculate the ultimate soil pressure. That means this will be the factor, because we take the size based on service load, as you see here, size based on service load, but the shear design and moment design will be based on factor load. So what we are doing now here, we are factoring the load divided by my area. So 1.2 dead load, 1.6, no, 1.2. Oh, let me check again. Is 100 is dead load or live load? 100 is dead load. Okay, so maybe when I was telling here, maybe I said this is live load, whatever it is. So hopefully you understood. So 1.2 dead load plus 1.6 live load divided by my final area that I took. Do not use this area because that is the needed and we are providing this. So this 5.87 KSF, this is key per square feet, is my factored pressure or factor load in terms of KSF. Okay, so we will use this for our shear design. Now, depth required for one-way shear. Yes, we saw one-way shear in our wall footing design also. One-way shear means like, okay, I'm making some space here. Maybe it is not going. Okay, so if I invert this function, it will look like this. It's kind of beam with lot of factor load. This load is 5.87 if I can remember. Uh, Now you can say keep per square feet, or if you assume the entire as your entire width as your width, then it can be keep per feet also. So whatever, let me see what your book used. Okay, we'll go there, but before that, what is one-way shear? We know that shear force is critical at d distance from the support. So at d distance, so we need to find our shear force here, and based on this shear force we will see whether this depth is good or no. Now d means always up to the reinforcement. So for foundation, my reinforcement will be here, so my d will be here to here. For this case, my reinforcement will be at the top, so my d will be here to here. So now we need to find the shear force here. We call this one-way shear because it is only one direction. So what is that? Simply this load 5.87 kip per feet times this distance. That distance should be, if I do this portion is 6.5 feet divided by 2, then I will deduct or half of the column and then did the distance. That your book or the solution did it. You can see here 6.5 by 2, it means at the at the middle of the foundation, then 6 by 12. 6 by 12 is the like 6 means half of the column divided by 12, so 0.5 feet. 13.5 is your d divided by 12. So if I go back to here, what it is doing, so here to here is 6.5 by 2 minus this half of the column 6 inch minus this 13.5 inch. So that it is doing. Sometimes it looks confusing, but it is very simple. Okay, then times 5.87. So this is feet, this is kip per feet square, multiplying is kip per feet. Now this kip per feet, again it is the width of the foundation. If you neglect this, that means if you consider, okay, let me, okay, again that is, there is something confusing or vague here. Actually nothing vague is let me make some room here. It is not going back. So that means if my foundation say this and my column is there, Now we are taking shear force here. So this is at d distance from here. Now if we assume entire b as this is an entire width, then you do not need that feet. But what your problem is doing, they are assuming a 1 feet strip, a 1 feet strip. So they are assuming this is 12 inch. They are assuming this 12-inch strip. This is what they are telling, keep per feet. Okay, so it doesn't matter. You can consider the entire. If you consider the entire, your b will be entire 6.5 feet. If you consider a small strip, your b will be 12 inch. So that is the key point. Now whatever you assume, both are right. So you can see here. Okay, then D required is BU to divide by phi to A prime CB. I hope that you know this, where it is coming. In foundation, only concrete will take the shear force. There will be no shear reinforcement. So how much a concrete can take? Concrete can take is this amount of shear force. We saw it from the chapter 8 shear force design. So in this design, we are calculating D required. This is the equation, and this is my shear force here. Okay, so if I go oh, where is my cursor? Yes, I got it. Yes, so this equation came from this. So it is 9539 pound divided by 0.75 to a prime c 12. See, you can they use 12. The reason is they are assuming 1 feet strip. If you use the entire, then your b will be the entire 6.5 feet, and in that case you must need to multiply by b also, that 6.5 feet, if you use the entire width as a b. Okay, or you can follow this book, but make sure that you understand that what you are doing here. Okay, why we convert into pound? The reason is this equation is in pound inch unit, pound and inch. So everything should be inch here, and the load will be pound here. So we are getting 9.68 inch. That means this is the depth we require based on this one-way shear. How much we are providing? We are providing 13.5 inch. So we are providing more. So it is good. Now it looks over designed. Yes, it is over designed. We can go back and change it, but there's something else to say in shear that is called punching shear. That is something new to this square footing. So here is the check for punching shear. Now what is punching shear? Hopefully you know the term punching. Punching means like uh, punching means like when you punch a paper, similar to that. That means if my column is here, if my foundation is here, if there's huge load here, dead load plus live load, so it may punch your foundation like this way. So this part will go up and this part may go down. That is called punching shear. Now for one-way shear, it is here. That means this portion may fail. Yes. So if I draw the profile of this, for non-shear, there might be a crack like this. There might be a crack like this. That is called uh, one shear, but this is called punching shear. Some part of the foundation will be punched. Now, based on experience, this distance is typically d by 2. So this portion is d by 2. So the entire width will be whatever the column plus d by 2 plus d by 2, or simply column plus d, column plus d. So this dimension, you will see this dimension in your calculation also. Okay, so if I go to the solution is, so first they did the B naught, which is perimeter of your punched area, what I showed, column plus D. This column plus D, where it came from, column plus D by 2 plus D by 2. That is the what dimension times 4, because 4 sides. If I go back there, you can, if I show the plan, so that is my footing, this is my column. So this perimeter, so 1 2 3 3 4, so 4 side, every side is column plus D. Okay, so now why it is d by 2? It is like based on experience. It is not like scientifically derived. Okay, so if I go there, so that is b naught. And what is your shear force? What is your punch shear force? That is something uh, critical or something to pay attention. How did they calculate? It is simply this 42.25 is our area of the foundation, minus the area of the punched area, that means column this 12 is column size, plus d is divided by 12. They made it into feet because this portion is in feet. So whole area minus the column area. Why it is square? Because the column is a square. So whole area minus the punched area times my load will be your keep. So if I go back to here, okay, so if I draw again, so what is this here? If I draw a big picture here, so the punched area is this. How they calculated? They took the entire area. Now I have my load here. I have my load here. This load is QU, which is 5.87 kg per square feet. Now this is the load. So how to calculate the punch area? That means if I draw the plan, yes, so we need to find the shear force in this border. How to find it? Shear force. What we are doing? We are taking the entire area minus this column area. That means we are considering only this portion and this portion all around. So from the entire area, if we deduct this area, our remaining is this area, this area. Then times this, we will get the shear force. So that they did. First entire area is 42.25 minus this punch area, which is column size plus d, and it is square. They divide by 12 to make it feet. So this 12 is to make into feet, inch to feet. But column size is 12 also. That is sometimes it might be confusing to you when you will solve your own problem. Make sure you understood. So if we so then the deduct of this and this will be my this area, the white portion, times my QU will be my punching shear force. So hopefully you understood. This is very critical, so I clarified it. Yeah. So this is 221 is your punching shear force. Now we will calculate what is the depth required for punching shear force. So this time my equation it will be 4. So there are two equation. One equation is this, other equation is this. So we should check both. Okay, so this equation, first we are using this equation. Now this is something new. You did not see it in your wall putting. It is in your book. So this is the equation or depth required for punching shear force. So there is 4 here. Last time it was 2 here. So be careful about it. So shear force in pound divided by 0.75 for F prime C B naught. So in this equation we use B naught because this shear force is all around the perimeter. So we are using B naught. Make sure it is not B. B naught, that means the perimeter of the punched area. 102 we calculated here. So after calculation, we found 13.22 inch is our required based on punching shear. How much we are providing? 13.5. So our it is very close, but it is less. We are providing slightly more. So we are still in good side, and they are very close. That means my design is very economic. Okay, we'll see the other equation now. There's other equation here, Bu2, that means the punch shear force. This is alpha S. You cannot see here alpha S, D B naught plus 2 A prime C B naught. This equation is in your book. It is another equation for punching. What is alpha S? Is a like constant. It is 40 for interior column, 30 for edge column, 20 for corner column. It is just a constant. So it is in your book. So our column did not say anything. So we are assuming it is interior column. So it is 40. If the problem says edge column, that will be 30. If the problem says it is a corner column, then it will be 20. Okay, so they used here alpha s is 40, d is 13.5, b not 102 plus 2, a prime c 3000. You cannot see 3 here, but it is 3000, b not 102. Then we'll calculate our d required. Now something confusing here, d here, d here. Ideally we cannot use 13.5 here. We should insert d here, then solve for d. But you can see that will be a very difficult equation. Like that will be a quadratic equation with a degree 2. But again, if we insert our initial d here, whatever the d you will get, it will be very close. It will be very close. So after calculating, they got 7.25. Now if we insert d here and calculate the d, maybe it will be 7.6, 7.1, very close to it. Now if there is a gap, like say we are providing 13.5, it requires 7.25. So we can tell that yes, it is good, because if I do the calculation exactly, it may not change so much. But say we are providing 13.5, after this calculation, if you find here 13.25, very close, that means you should do the actual or accurate calculation. In that time we may use exact d here and then solve for d. But yet there is a gap here, 13.5 versus 7.25. We will not do it. And just to let you know, most of the cases this criterion doesn't win. This is the mostly winning criteria. So we can calculate that, okay, our d provided 13.5 inch is good, because other cases we need less. So our design for shear is done. It is all about the depth, whether our depth is good or no. That is our shear design. There is no shear reinforcement. So now we will do our moment design. Design of reinforcement for moment. So if I go back to my uh, sketch, okay. So what is moment design? So this is our column. There will be reinforcement here. We will design this reinforcement based on this shear. So what we will do? We will assume this is a cantilever beam, and cantilever beam we will design only in this portion. Now, so this will be our lever arm. So actually, what we are doing? We are assuming a cantilever beam. Cantilever beam. So we are designing this, and this portion is same. So how to find the moment here? Say this, if this load is say Q, and it is a uniformly distributed load, so Q times this distance, if it is say X, Q times X is my load. It is acting at the middle. That means my moment will be Q times X times half of this X. This distance is X by 2. So that is the moment equation. QU X square by 2. That is the moment equation for a cantilever beam. Now how to find X? Very simple. If I see the or I can do here. So this portion is 6.5 divided by 2, 12. Oh, I do not need divide by 12, divided by 2 is feet. This is this distance. If I deduct this column is 12 inch divided by 2 or 1 by 12, then this is my feet. So this 2 means half of this. This 12 will convert inch to feet. This 12 is column size. Okay, you will see that your book did the same thing. If I open it, so lever arm is made that X 6.2, 6.5 by 2, then half of the column 2.75. Then they calculated the moment is whatever I showed you. It is 22.2 feet cube. Then once I know my moment, once I know my size, I can calculate this mu by pbd square. Make sure this should be in pound inch. So it was 22.2. They multiply by 1000 here, and then they multiply by 12. So it is now pound inch divided by 0.9. B is 12. Why B is 12? Because they assume 1 feet strip, and then d square. Sometimes people forget the square here. It's bd square. They got 135. Then go to the table. Now which table will give you base? It depends on f prime c and fy. So f prime c and fy, if I open your book, it is most probably table appendix A12. I'm not sure. Okay, I'm opening the book. A11 is 50 and 4 psi. Table A10 is 50 psi, 50,000 psi and 3,000. Not this one. What about 12? Yes, it is 12. Fy 60,000 psi and A prime C 3,000 psi. So from that table, we will check our rho. So our rho is 0.00232 based on this number. If you go to the table, you will find it. And this value, now you can check with this or you can check with the minimum rho. What is rho mean? That you will find it in table A7 or A8. A7. So you can check this rho whether it is more than the minimum or less than the maximum. So you can go to table A7 to check this. And they checked it, it is okay. Even I checked it for 3060 grade, minimum is 0.0033 and maximum, that means when tensile strain is 0.005, is 0.0136. So it is more than minimum, less than maximum. So good. Then AS is rho B. Now do you know why it is B? Why now it is 78? Because this time they are taking the entire width. If I show you this, so this is my column. Oh, it looks like a rectangular. Okay, I will change it. So this is my footing, this is my column. Now this time they are taking, this is the entire width, 6.5, it is 75 inch. So if you use this as a B, you will get reinforcement for the entire width. That means whatever the reinforcement you need to place it here, and it is, as it is square, both way it is same. This time they are taking entire width. If you take a strip, 12 inch strip, it will be okay. Whatever you will get the reinforcement here, you have to copy paste all around. That is the concept. Okay, so they used entire 78 and D. So they got 3.5 on, and from table A4 they selected, yes, 6 number 7 bars. That means they are providing 3.6 inch, slightly more is okay. What will be the spacing? 78 minus 2 side of 3.5 inch. That means it is the clear cover. Divided by 6 minus 1. Okay, where they're getting. So if I, that means this is the entire putting, then they are providing 6 number 7 bar. So 1 bar here, 2 3 4 5 6. What they are doing, they are deducting 3.5 inch here, 3.5 inch there. So total is 78 inch minus 2, 3.5 inch they are deducting. Whatever available, 1 space, 2 3 4 5 space, that is the 5 here. That will be our center to center spacing of the bar. Why do we need it? We need to check the minimum spacing and maximum spacing. Now this will be same thing this way also, because it is a square footing, both direction reinforcement will be same. Okay, they found 14 inch. Yes, it is less than the maximum. Maximum is, we know that 18 inch or 3 times the depth, and minimum is 1 inch or bar diameter. So it is clearly less than the maximum, more than the minimum. Then development length. Now, so far we did not cover this concept, but if you know anyhow, you can check it, say the development length, or if you do not know, we will cover it in a different lecture. But what is that? Let me tell you very briefly. Development length means So okay, if I draw the mm, column again, my load is here, load is there. So this is the point where my moment is maximum. So when I'm providing the reinforcement, I need to have some length to develop the bonding in this reinforcement. That length is called development length that required. Now I should check that whatever space I have here, I forgot how much, most probably 2.75 feet. When I calculate the moment, I can remember. It may be wrong, but something like that. I should calculate that I have development length more than this. If I do not have it, what to do? I can make it a hook. Or if this also, then we can calculate this development length as a hook. Then we have to check it. Still, the if the space is not sufficient, we can make the bar like a 190-degree, sorry, 180-degree hook. We can make this kind of hook. We can make this kind of hook. So we should check it that whether our reinforcement will be linear or this kind of hook or this kind of hook. So we have to check that that spacing. But most of the cases it should be okay. If it is not okay, there are some remedy. One remedy is you can do this kind of hook, other remedy you can do this kind of hook. For this case you need less development length. There's another way. You can decrease the bar size. If say now you are using number 7, if you decrease the bar size, some for a smaller bar, a smaller size bar, you need less development length. Why? A smaller size bar, it has greater surface and area. Okay, the reason is we need more bar. Okay, that is different. We will discuss it later. Also, there's other way. If it doesn't work, then no option. If I try all option, then we have to increase the footing size, but that is very unusual. Okay, so if you do hook, most of the cases it should be okay. So that is the check for development length. So our design is more done. uh, so then what is our final step? Final step is to detailing means always so show your design in neat sketch so that the field labor or field engineer can identify. So what is the neat sketch? So draw a plan view and so 1 2 3 4 5 6 6 bar or 7 bar, 6 bar. So tell it 6 number 7 bar, tell this is 6.55 feet, till this is 6.5 feet, show that this is 3.5 inch, this portion is 3.5 inch. uh, so this here also 1 2 3 4 5 6 6 bar, show both. Also show the profile clearly. So this portion is 16, this portion is 18 inch, reinforcement will be here, this depth will be 13.5 inch, and that will be also 6 bar. So this bar and this bar both 6 number 7, and this is 12 inch your column. So this way, and this is 42 inch of backfill. So this way show your design in a very neat sketch. In your exam, at least provides something like this. It doesn't need to be in scaled, but at least provide some sketches of your design. So hopefully you understood what is square footing design. There's something difference with the column. In column, we do not need punching shear. In column, we do not need punching shear, but in square footing, we need this punching shear. Now, what about for rectangular footing? Exactly same thing. We need the punching shear for rectangular footing. There will be only difference will be the reinforcement arrangement. So I'm not going there. In the next video, I will show a rectangular footing, but very briefly the difference will be, so rectangular footing this way my reinforcement will be one calculation, my say footing here. In this way most of the reinforcement will be here, some will be here. That is the difference. So in this side all reinforcement will be homogeneously spaced. In this side there will be bandwidth, we call band bandwidth. In this bandwidth my reinforcement will be higher. Outside this my reinforcement will be in this side, and in this side reinforcement will be lower. That is something different from square footing to rectangular footing. So we will see you then. Thank you.